Hello friends, now we are going to discuss about the concept as angular momentum. As we know, in translational motion, a linear momentum denoted by P of any body is the product of mass of that body and its linear velocity v. So the equation of linear momentum P is equal to m into v. And in vector form, we can write vector P is equal to m into vector v. Uh, Angular momentum in a rotational motion is analogous to the linear momentum in translational motion, and that angular momentum is the product of moment of inertia and its angular velocity omega. It is denoted by L. The equation of that angular momentum L is equal to I into omega. In vector form, vector L is equal to I into vector omega. Now, how we can derive this equation? So, for the derivation of angular momentum, we see the figure. This is the rigid body. The rigid body is made up of n number of particles. They are moving. They are actually present at a particular positions. Now, the body is rotating about their mean position of a axis passing through the point O, perpendicular to the plane of figure in anti-clockwise direction. The mass of rigid body is denoted by m. The rotational angular velocity of this body is omega in anticlockwise direction about the axis passing through the point O. N number of particles are present here. The particle number first is m1, second one is m2, third one is m3, up to the last one is mn. And they are present at a distance of r1, R2, R3, R4, R5 up to Rn respectively from the axis of rotation. All the particle moves in circular path. Because of that circular motion or rotational motion, all the particle perform circular motion. And while in circular motion, the angular velocity of all the particle becomes same, that is omega. But because of different radii about the axis of rotation, the linear velocities are not same, they are different. So as body rotates, the first particle whose mass is m1, which is a revolving along the circle of a circumference whose radius is r1, then its linear velocity of that particle v1 is equal to r1 omega. Now the linear momentum of that particle p1 is equal to m1 into v1, but v1 is r1 omega. So that the equation is m1 r1 omega. Similar to that, the moment of linear momentum of a particle about the axis of rotation. What? The moment of linear momentum of a particle about the axis of rotation is defined as the product of linear momentum and the moment r. So we can write this equation as a moment of linear momentum is equal to linear momentum into moment r. So moment of linear momentum of particle first whose mass is m1 is given by L1 is equal to p1 into r1, where p1 is the linear momentum and r1 is the moment r. Now p1 is m1 r1 omega, and this value is r1, so that it becomes m1 r1 square omega. Similarly, moment of linear momentum of a second particle of whose mass is m2 and which is situated at a distance of r2 from the axis of rotation, that moment of linear momentum is L2. L2 is equal to P2 into R2, that is m2 r2 omega into r2, that is equal to m2 r2 square omega. So in this way, all particles means moment of linear momentum of all the particles can be calculated. Now, sum of all the moment of linear momentum is equal to the angular momentum. So angular momentum about the axis of rotation is equal to total moment of linear momentum. So that we can write this equation: L is equal to L1 plus L2 plus L3 plus up to Ln. Now put all the values of L. So L is equal to m1 r1 square omega plus m2 r2 square omega plus m3 r3 square omega plus up to mn rn square omega. Now take common omega from all the terms. So L is equal to m1 r1 square plus m2 r2 square plus m3 r3 square plus up to mn rn square into omega. Now this bracket is nothing but the summation of I is equal to 1 to L mi square into this omega. This bracket is a moment of inertia. So in this way we can derive this equation. L is equal to I into omega. So angular velocity or angular momentum of a body is the product of moment of inertia and its angular velocity. The SI unit of angular momentum is kilogram meter square per second, or in the CGS gram centimeter square per second. Now we'll see the principle of conservation of angular momentum. What is that law of conservation of angular momentum? So the angular momentum of a body remains constant until the external force is not acting on that body. So this is the law of conservation of angular momentum. How to state that law? If no external torque acts on a rotating body, the angular momentum of a body remains constant. So how to derive that particular law of angular momentum? So as we know, torque tau is equal to I into alpha. That is a relation between torque and angular acceleration. Tau is equal to I alpha. But alpha is the angular acceleration, is the rate of change of angular velocity. So alpha is equal to d omega upon dt. So put this value of alpha in this equation. Tau is equal to I into d omega upon dt. Now, moment of inertia of a body about a given axis is constant. So, we take this term inside this. So, we can write as a tau is equal to d by dt of I omega. But I omega is a L, that is angular momentum of that body. So, we can write here tau is equal to dl upon dt. That is torque is equal to the time rate of change of angular momentum. But if no external torque acts on the body, means tau is equal to 0, then the differentiation of that angular momentum dl upon dt is equal to 0, and the differentiation of any term with respect to that value is equal to 0, then this particular variable is constant, that is L is constant. So dl upon dt is equal to 0, so that we can say here L is equal to constant. So angular momentum of a body remains constant if no external torque acting is acting on it. So this is the law of conservation of angular momentum. Now we have some examples of law of conservation of angular momentum. The first example is very interesting example. Actually, these are the two pictures here. A girl rotate about the axis of rotation by stretching her hands, and in the second figure, the hands are closer to that body. So, what will change which are observed in these two cases? We'll see in detail. That when an ice skater is spinning on the tip of her skate with her arms are extended, then the angular momentum is conserved because net torque on her is negligibly small. Means it rotates with angular velocity omega because of the angular, what we say, the moment of inertia of I. But in this next case, her rate of spin increases when she pulls her hands, arms towards that body. So what will happen when the particular girl, when girl pulls her hand towards the body? So moment of inertia of the body decreases, and according to that decrease in moment of inertia, it increases angular velocity. So in this case, we can say that the rate of spin increases greatly when she pulls in her arms and decreasing her moment of inertia. So the work she does to pull in her arms result in an increase in rotational kinetic energy. Okay, so this is about to change in angular velocity due to the change in the moment of inertia of that body. Now another examples are there. There are some examples. So tornadoes are the one example. Storm system that creates tornadoes are slowly rotating. When the radius of rotation narrows, even in a logical region, angular velocity increases and sometimes to the serious level of a tornado. Earth is also another example. Our planet was born from a huge cloud of gas and dust. the rotation of which came from turbulence in an even large cloud. So gravitational forces caused the cloud to contract, and the rotation of it increases as the result. So this is about the rotational dynamic 1 and 2. Thank you.